Hope you all had a great midterm break. So the first half of this course has had us venture from the realm of the ancient Greeks. We saw the proof of the fundamental theorem of arithmetic, Euclid's lemma, and after that we followed that material by talking about modular arithmetic and using that language to go back and prove statements like Fermat's Little theorem, its generalization, Euler's theorem. We talked about Chinese remainder theorem, and we have seen it being used a handful of times now. In the last couple of weeks, we started venturing into quadratic residues, multiplicative residues, and that's where we are going to be staying for the next week and a half, where the goal is to prove the law of quadratic reciprocity, which we will state at the end of today's lesson. The first half of today is going to have us prove Fermat's sum of two squares theorem. So the proof that we are going to cover is going to be very similar to the one that Euler originally did, of course simplified because we have modular arithmetic at our disposal. And the one big difference between the proof that we will do and the one that Euler did is in what is known as the reciprocity step. And so the proof is broken down into two arguments. So one argument is the one that is here on the screen, the Euler's descent lemma, and so this dates to 1747. And then the second statement is the reciprocity lemma, which is stated here. The reciprocity lemma was actually the statement that took Euler the longest time to prove, and he spent a considerable amount of time working on it. And we know from his letters that this was something that he spent years working on, even before having done the descent lemma. The argument that we will do, because we have already knowledge of the quadratic character of -1 from the last lesson, will be simplified, and so this argument will actually be simple for us, whereas the descent lemma will be involved. And so with that, we will go ahead and finally lay to rest the famed conjecture of Fermat, the sum of squares theorem, that if we have an odd prime, then p is equal to a squared plus b squared for some natural numbers a and b, if and only if p is congruent to 1 mod 4. And so that's the goal for the first half of today's lesson. But I will also mention that as we proceed further, we're going to be talking about quadratic reciprocity, of course, but after that, we're going to talk about the Gaussian integers. And in that realm, we'll see a different proof of the Fermat sum of squares theorem. And so this will be around week 8. And in the last week and a half, we're going to venture into what are known as modular forms. And through that, we're going to go ahead and sketch another proof of the Fermat sum of squares theorem. And so by the end of the course, we will have seen 3 different ways of proving this result. So let us go ahead and get started. So the first thing for the Euler's descent lemma. So here we have a natural number. We are assuming that it's a sum of relatively prime squares. And our assumption is that if we have a prime dividing n, then that prime must also be a sum of relatively prime squares. So how do we prove this? So let's go ahead and eliminate the easy cases first. So what happens if p is equal to n? Then there is nothing to show, because it's gonna, by assumption, it will be a sum of relatively prime squares. So if p is equal to n, then the result follows. By assumption. And if p is equal to 2, there's nothing to show, because 2 is equal to 1 squared plus 1 squared. And so it remains to consider the case when p greater than 2 is prime. So we're looking at the odd primes. And so then what we are going to do is do this via contradiction. So let's go ahead. So towards a contradiction, suppose that p is not a sum of relatively prime squares, And so this is going to be our contradiction assumption. So with this assumption, now we're going to go ahead and construct a set. So now let S be the following. So it's going to be the collection of Q greater than 2 is prime. So this is a set of prime numbers such that Q is not a sum of relatively prime squares, and there exists natural numbers x and y with the GCD of x and y being 1, so they're relatively prime, and Q dividing x squared plus y squared. So by our contradiction assumption, we have that P is a prime that is not a sum of relatively prime squares, but we also know that P divides n, which is a sum of relatively prime squares, and so our n in this case would be equal to x squared plus y squared. And so by our contradiction assumption, we have that P is an S, and thus S is non-empty. And since, of course, S is a collection of prime numbers, so it's going to be a subset of the naturals. So the Wall ordering principle applies. And so S has a least element. Now what we are going to do is something that is common. We want to continue using the letter P. So we're going to do a relabeling if necessary, because all we know is that P is an S. So we can go ahead, choose the least element, and doing a relabeling, if it's not the least element, we'll call the least element P. And so relabeling, if necessary, we may assume that P is the least element of S. So we have our least element. By assumption, so by assumption, P divides n with n equal to a squared plus b squared for some natural numbers a and b, with the GCD of a and b being equal to 1. So that's what we have by our assumption. And now what we are going to do is apply the division theorem to both a and b. So we claim that there exists Q, let me go ahead and write this Q1 and Q2, and then R and S in the integers, such that A is equal to P times Q1 plus R, and B is equal to P times Q2 plus S. So of course, here I wrote claim, but we know we can always write it in this way. The thing about this is that we want something stronger than what the division theorem asserts. Technically, it's going to be equivalent, but we want R and S to satisfy the following: with the absolute value of R and the absolute value of S to be strictly less than P over 2. So notice that P is odd, so P over 2 is not an integer. So we want to show that the existence of these. the way that this proof is the way that the claim will be justified, we only need to show it for A, because if we show it for A, the same exact argument is going to hold for B. So let us go ahead and show the claim. So by the division theorem, there exists, let's go ahead and call it Q prime and R prime, integers, such that A is equal to P, Q prime, plus R prime, with 0 less than or equal to R prime, less than P. So we have this here. So that's by the division theorem. If R prime is less than P over 2, then we can take, actually, just to be, I put absolute value, but keep in mind R prime, we're using division theorem, this is non-negative, but I went ahead and just removed the absolute value. So if R prime is less than P over 2, so we can take R prime to be equal to the R that we want. And so that will show the claim. So suppose that R prime is greater than P over 2. So we don't have to show the equality, because as I mentioned earlier, P is odd, so P over 2 is not an integer. So we just have to consider R prime is greater than P over 2. That's the only other possibility we have for what R prime can be. And so now, let's go ahead and observe that A is congruent to R prime mod P, but this is also going to be congruent to R prime minus P mod P, since P is going to be congruent to 0 mod P. So what we're going to do now is take the inequality, this here, alongside with R prime being less than P, and we're going to subtract P from each side of that inequality. So subtracting by P gives that we have, so we have on the left hand side, we're going to have P over 2, so we're subtracting that by P. That's going to be less than R prime, which we're subtracting by P. And on the right hand side of the inequality, we have that this is less than P, so we have P minus P, so this is 0. And so our quantity will always be negative. And now since P over 2 minus P, well, P is just 2P over 2. So we can go ahead, factor a P over 2, and this becomes a minus 2, a 1 minus 2, which is negative P over 2. We get that the absolute value of R prime minus P is going to be less than P over 2. Since this is negative and we know that it's bounded on the left, so in other words, R prime minus P is greater than negative P over 2. And so now we have the absolute value that we want. So now we can go ahead, and what we are doing is just going back to our equation for A, and so we're going to take our R to be R prime minus P. So then A is equal to P times Q1, but we subtracted if we want to subtract a P, we want it to be cancelled off, so we're going to add a P, we're going to add a 1 over here, and then we're going to do, I meant to have a Q prime here. So we're looking at our equation over here for A. So we're looking at our A is equal to P Q prime plus R prime. So we want to subtract the P, but we're going to go ahead and add a P over here. So we're going to have P times Q prime plus P plus R prime minus P, so that we have the same exact equation. And so that's the same as taking P times Q prime plus 1 plus r prime minus p, and so the claim holds by taking q, and so we call that, in the claim, we call that q1. So we can take q1 to be q prime plus 1, and we take r to be r prime minus p. And so we have our claim for A, but as I mentioned, the argument we just did, there's nothing special about A. With B, we can run the argument verbatim, and we get the same exact argument, so the same will hold for B. Alright, so let's do a recap. We constructed our set S, and we chose our prime P to be the least element of the set S. So P is not a sum of relatively prime squares, but it divides a sum of relatively prime squares. We have constructed that P divides n, which is equal to a squared plus b squared, and we now know that A can be written as P times Q. A is equal to P times Q1 plus R. B is equal to P times Q2 plus S, where Q1, Q2, R, and S are integers. But we also have that Rs, those in absolute value, are strictly less than P over 2. So now, let's go ahead and do the following. So observe that if we take a squared plus b squared, then this here, by our properties of modular arithmetic, we know that a squared is going to be congruent to r squared mod p. And so we have that this is congruent to r squared. But then doing the same thing for b, we get that that's congruent to s squared. And so we have this congruence. So we have that this here is congruent to r squared plus s squared mod p. Now, because p divides a squared plus b squared, this is congruent to 0 mod p. So therefore, this is going to be congruent to 0 mod p. And so thus, p divides r squared plus s squared. But p does not divide r or s. Because if p divided r, then this will be congruent to 0 mod p. But then we must have, since all of this is congruent to 0, that s is also going to be divisible by p. So we know that p does not divide r and s. So we got that statement there. So now let's go ahead. So take m to be equal to r squared plus s squared, and let d be the GCD of r and s. Then we have that m over d squared is equal to r squared over d squared plus s squared over d squared. So what we have done, we know that d is the GCD of r and s. So then d squared divides r squared and s squared. So we can divide this side by d squared, and we know that then by linear combination lemma, d squared divides m. And so we have that m over d squared is equal to r squared plus d squared, r squared over d squared plus s squared over d squared. And so m over d squared is a sum of relatively prime squares, and p divides m over d squared. So we're going to do another relabeling. We're going to change our labeling again. So what we want is to consider these over here. But we know that this here, r squared over d squared, s squared over d squared, we divided by the GCD. We can go ahead and take these to be the congruences for r and s. So relabeling if necessary. If necessary. We may assume that the GCD of R and S is equal to 1. Because if it was not, we can go ahead, do what we just did here to get that m over d squared is a sum of relatively prime squares, and we can just take those to be, this to be our R, this to be our S, and then m would just be r squared over d squared plus s squared over d squared, sum of relatively prime squares. So we're going to go, now, so we have this assumption here. But now, what is our assumptions on R and S? Well, we show that in absolute value, that absolute value of R is less than P over 2, and so is absolute value of S. So now observe, and so so we have over here, we have M, which is P squared, R squared, jumping ahead. So we have R squared over S plus S squared. But now this is going to be less than, R is less than P over 2. So because this is R squared, it will be less than P squared over 4. So we get P squared over 4. And then we get for S that S squared is also P squared over 4. So adding that together, we get P squared over 2. So we get this here. And so we have that M is strictly less than P squared over 2. And P divides M. And so we get the following. And so here is where the fun begins for the proof, and how everything ties in to get the desired conclusion for the descent lemma. We're going to look at now at W, which is M over P. And the way we construct it, and this is where this assumption we did over here by taking the absolute value of R and S to be less than P over 2 comes in. Because now what we have is that W is equal to M over P, which we know that M itself is less than or equal to P squared over 2. So if we divide by P, we have M over P, and then this is going to be less than P squared over 2 divided by P. So in other words, P over 2. So we get that W is less than P over 2. And now, we're going to go ahead and consider the prime factorization of W. So let W equal Q1, Q2, all the way to QL, where each Qj is prime. So the way that we are writing it here is we're just writing it in terms of its prime factors. So we could definitely have repeats over here. But what we know is, but from the inequalities we have, we can deduce things about these Qj's. So in particular, so actually I should say by construction, so by the above, Qj is going to be less than P over 2, because we know that each Qj divides W, and W is strictly less than P over 2, so each of those prime factors has to be less than P over 2. And then of course P over 2 is less than P. And we also have that Qj divides R squared plus S squared. And so both of these conditions hold for each J. So now we have Qj is less than P, and it divides R squared plus S squared, but R squared plus S squared, that is a sum of relatively prime squares. So how does this tie in with our assumption at the start of our, so we constructed this set S. And so S is the collection of those odd primes such that Q is not a sum of relatively prime squares. And there exists relatively prime squares which Q divides. So right now, what we have is that there's two possibilities. Qj could be equal to 2, in which case it's a sum of squares. So let's write that down. If Qj is equal to 2 for some j, then it is a sum of squares, since it's just going to be 1 plus 1. And if Qj is odd, so if we have an odd prime, then we are going to have a problem, because we have that we're dividing a sum of relatively prime squares, and so that's from our S, but we also know that P was chosen to be the least element of S. So that means that our Qj's cannot be an S, because if Qj was an S, then we would contradict the minimality of P. So if Qj is odd and Qj is an S, then we would contradict the minimality of P, since Qj is less than P for every j. So consequently, Qj is not an S whenever Qj is odd. So thus, each Qj is a sum of relatively prime squares. And so now we have that if it's even, it's a sum of relatively prime squares, 1 and 1. But if it's not even, then we can go ahead and also have that it's a sum of relatively prime squares by the construction of S. And now we go back to the statement we proved at the end of our last lesson. So recall that if we have a natural number n, and Q is a prime factor of n, which is also a sum of relatively prime squares, which is what we have right now for each of our Qj's, then n over Q is a sum of relatively prime squares. So let's go ahead and apply that. So this is by lemma 1.16.2. So by lemma 1.16.2, we will have the following, that m over Q1 is a sum of relatively prime squares. And then repeatedly applying the lemma, will yield the following, that if we take m over Q1, well, we know that m over Q1 is a sum of relatively prime squares. So if we take the lemma again and apply it to Q2, we will get that m over Q1 times Q2 is also a sum of relatively prime squares. And then we apply it to Q3 all the way until we get to QL. So in other words, we're looking at m over the product of Q1 through QL, which is what we define to be W, which is equal to, drumroll, P. Because we constructed W to be m over P. And so now we have that P is equal to m over W. And so P is now a sum which is a sum of relatively prime squares. And thus, P cannot be an S, which is a contradiction. So we have finally finished off the descent lemma. So now that we are done, I just want to go ahead and mention a couple of historical comments. So this proof is very similar to the one Euler did, but not exactly the same. Of course, we use modular arithmetic at some points in the argument. But more importantly, we did it in the language of set theory. We constructed a set. And the thing with proofs back in the 1700s and even 1800s, they were not done in the language of set theory. That came with the work of Cantor in 1874. And so the way that Euler did this proof is a method that via the ordering principle we don't tend to see. And it's a proof method due to actually Fermat. The only proof that Fermat ever wrote down pioneered this method, which is the process of infinite descent. To get where the name is coming from, let's go ahead and analyze the proof. We did our argument by constructing a set S and then choosing a minimal element. But if we had not constructed the set S, we could still, by our assumption, assume that we have a prime. So we do the contradiction assumption, so we can assume that we have a prime P that is not a sum of relatively prime squares. And so infinite descent, the idea is the following. So we start off with our P without using the fact that it's the minimal element of S as we did. We proceed through the same argument we just did. And once we get to this statement over here, where we get M, W is equal to M over P, we write W in terms of its prime factors. And so now we are left with the following, where we know by lemma 1.16.2 that if each of the Qj's is a sum of relatively prime squares, then we will have that M over the product, so W, that M over W is equal to P is a sum of relatively prime squares. That would be a contradiction. And so that means that because P is not a sum of relatively prime squares, one of these Q's cannot be a sum of relatively prime squares. So relabeling if necessary, we can take it to be Q1. So now we start the proof again. So now we take our Q1, it's less than P, and so now Q1 is not a sum of relatively prime squares, but it divides a sum of relatively prime squares. So we run through the same argument, where now we just replace P with Q1, and M with the corresponding value that we will get, so let's call it M1. And so we're going to come down to this to the step over here, and we're going to have M1 over Q1 is equal to some W1, and then we come to the lemma 116.2, and so because Q1 is not a sum of relatively prime squares, there must be a prime factor of M1 over Q1 that itself is not a sum of relatively prime squares. So let's go ahead and call that Q2. And so we have this chain of inequalities. And so the idea of infinite descent is we're just doing the same argument over and over again, each time producing a new prime number that is strictly less than the former one. But if we continue this process ad infinitum, this is impossible because there is a least natural number, there's a least prime. So this cannot go on forever. So it cannot go on forever, and so this will be the contradiction. And so that's how Euler got his contradiction here, is that he constructed this chain of primes, each being strictly less than the previous one, and therefore getting his contradiction because the primes are all positive natural numbers. And so this is the method of infinite descent. The nice thing about the ordering principle is that it's essentially infinite descent in disguise because we're putting it into our set S that we construct using that contradiction assumption. So now we have Euler's descent lemma, We need one more statement and we will have Fermat's sum of two squares theorem. So before getting to Euler's reciprocity lemma, let us recall the quadratic residue of -1. And so it's rather silly because this argument will make Euler's reciprocity lemma just follow automatically. And so the quadratic residue of -1 tells us that if we have -1 on P, then it's equal to 1 if P is congruent to 1 mod 4. So let us go to the reciprocity lemma. So we have that by assumption P is congruent to 1 mod 4, and we want to show that P divides a sum of relatively prime squares. Here's the proof. So that was Theorem 115.4. So by Theorem 1.15.4, -1 on P is going to be equal to 1, since P is congruent to 1 mod 4. So therefore, there exists, so by definition, because this is the Legendre symbol is equal to 1, so therefore there exists some x bar in the integers modulo P such that x bar squared is equal to -1 bar. And so thus, x bar squared plus 1 bar, is equal to 0 bar by equivalent statements for congruence. We have that P x squared plus 1, and so now we're dropping the bar, so we're going back to the whatever x squared is. X squared plus 1 is going to be congruent to 0 mod P. So therefore, P divides x squared plus 1 squared, which is a sum of relatively prime squares. And so we got the proof. And so we got Euler's reciprocity lemma. And so this concludes the proof because, of course, the GCD and since just being pedantic here, this is just 1. And so QED, we got it. And so it's surprising with how much we have proven up to this point in the course that this lemma that took Euler years to prove, and as you saw, the descent lemma was done in 1747, 2 years prior, and it would still take him 2 years after that for Euler to prove this statement. And upon proving it, he would write to his friend Goldbach and wrote that and told him, "Now have I finally found a valid proof of Fermat's sum of squares theorem." And so, as we will see in the next slide, this statement, together with the descent lemma, finishes it off for the Fermat's sum of two squares theorem. So here's the proof. So let's go ahead and do the forward direction. So this one requires nothing fancy, just looking at this modulo 4. So suppose P is equal to a squared plus b squared. We know that P is an odd prime by assumption, but because P is prime, sorry, not because it's prime, since P is odd, one of A or B must be even. So without loss of generality, suppose A is even, then P is going to be congruent to A squared, which is going to now be 0, and so P is going to be congruent to B squared mod P. And we actually have, so A is even, and of course the other one is odd, so I'm just going to write that there to have everything in here. and b is odd, but b squared is going to be congruent to 1 mod 4, since 1 is the only odd quadratic residue. Of the integers modulo 4. And so we have this here, and so thus p is congruent to 1 mod 4. So we got the easy step. So let's do the converse, which is the hard case, but now we've broken it up into these two lemmas, the descent lemma and the reciprocity lemma. So putting those together, we're going to get the result. So suppose p is congruent to 1 mod 4. Well, if p is congruent to 1 mod 4, the reciprocity lemma tells us that p divides a sum of relatively prime squares. So p divides a sum of relatively prime squares. So we get the first part. But now we have that p divides a sum of relatively prime squares. And now we apply the descent lemma, which tells us that if p divides a sum of relatively prime squares, it itself must be a sum of relatively prime squares. And so we're done. P is a sum of relatively prime squares. And we got this. And we have laid to rest one of Fermat's conjectures that took a century plus to prove. And while these are monumental results, the fascinating thing is that 150 years later, Richard Dedekind will come across a new proof that uncovered that this statement is really a property of what the prime numbers are in a new system of numbers, which we will call the Gaussian integers. And so this will be the topic that we will get to after we finish the proof of quadratic reciprocity. But that's it. We have finished off the first of our 3 proofs of Fermat's sum of squares theorem. And so let's go ahead and talk about what happened after for Euler. So 1749, he finishes this statement of Fermat. But Fermat actually wrote down a couple more conjectures, or things that he claimed to have proven. So Fermat, alongside claiming to have proven the Fermat's sum of squares theorem, also claimed to have proven the following. That p is equal to x squared plus 2y squared, if and only if p is congruent to 1 or 3 mod 8. And that p is equal to x squared plus 3y squared, if and only if p is equal to 3, or p is congruent to 1 mod 3. So it would take Euler 10 years after his proof of the sum of squares theorem to do the case when p is equal to x squared plus 3y squared. And one of the final projects, if you're interested, will have you go through the argument that Euler did. And it really boils down for both of these two results. If it's going to follow a similar process to this one. There's going to be a descent lemma and there's a reciprocity lemma. And so both proofs are structured very similarly, except that for our purposes, since we are armed with quadratic reciprocity, the reciprocity steps will be the easiest cases, which for Euler was actually the other way around. The descent lemma was easy. The reciprocity statement was the hard part. But we are in luck. And so Euler realized that these two statements are related to the Legendre symbol. And so, and this is one of the questions on the exam. P divides x squared plus ny squared, where x and y are relatively prime, if and only if negative n on p is equal to 1. And so he was aware of this here. But being aware of that still made it significantly hard to find exactly how to conclude these congruences for p congruent to 1 or 3 mod 8. And so in our case, we had the quadratic character of -1 on p is equal to 1, if and only if p is congruent to 1 mod 4. And so that's what's missing. We have this here, but then we still have to figure out what primes satisfy those conditions. And in the case of 2, it's surprisingly worse because we have to talk about what is a quadratic character of 2, which we will also be talking about in the next week. And so this case here will take Euler quite some more time. So now we're looking at a work that he worked on for over 20 years in establishing. But with both of these works, he settled the claims of Fermat pertaining to which numbers can be written in the form x squared plus 2y squared, 1y squared, and 3y squared. But years prior, so now let's go back to 1744, before he had proven these results, he was already investigating what would be necessary to prove these results. So specifically, this theorem was known to him as early as 1744, and in fact, he came upon his famous conjecture. So based on numerical computation, he realized that if we look at the Legendre symbol of -3 on p, then this is going to be exactly, -3 will be a perfect square mod p, precisely when p is congruent to 1 or 7 mod 12. And then he made similar statements for -7, 5, -5, 3, 7, and so forth. And with that information, he saw a pattern arise. And so one of the homework questions that you had you come upon looking at Legendre symbols based on 2 odd primes. And what Euler realized is that q on p is equal to 1 if and only if p is congruent to plus or minus beta squared, where beta is an odd integer, mod 4 times q. And so this is the statement that Euler conjectured, and would it later be proven by Gauss in what we call the law of quadratic reciprocity. So now we make it to Gauss's Aurum Theorema, the law of quadratic reciprocity. And as I mentioned, this is equivalent to Euler's conjecture, but these two forms are the one that we will be focusing on, as they lend themselves better for computation and for getting theoretical results, such as what are those primes such that -3 is a perfect square mod p. And so we just saw this with Euler's conjecture. And so using these two formulations that we just saw, we can actually go through and prove these statements explicitly. Whereas with Euler's conjecture, while it can be done, it's a bit more involved. And so at the end of this lesson, we're going to go ahead and deduce that -3 on p is equivalent to p being congruent to 1 or 7 mod 12 by utilizing the restatement of the law of quadratic reciprocity, Theorem 1.16.11. So what does the law of quadratic reciprocity state? So we have two forms here. So in both cases, we have the same assumption. We have p and q. They are odd, distinct primes. So in the first formulation, we have that if p is congruent to 1 mod 4, or q is congruent to 1 mod 4, then their Legendre symbols are equal. Q on p is equal to p on q. However, if p and q are both congruent to 3 mod 4, then their Legendre symbols are different in signs upon flipping. So namely, if we have q on p, then that will be equal to the negative of p on q. The second form, which is the restatement, has a more compact feel to it. And what it says is that if we look at the product of the Legendre symbols q on p times p on q, then that's just going to be equal to -1 to the p minus 1 over 2 times q minus 1 over 2. And so we'll get some familiarity with working with this one. And so of course they are equivalent to Euler's conjecture, which we have seen. And now let's go ahead and prove that they are equivalent. So let's go ahead. And so I'm not going to do 1 implies 2, as this will be part of your homework. So this is in 11.3.2. So that's going to be 0.12. And so you'll be doing that for homeworks, but I'll go ahead and do the rest. So let's go ahead and show that 2 implies 1. And so for 2 implies 1, so we're going to assume Theorem 116.11. And we're going to proceed by cases. And so namely the cases corresponding to Theorem 116.10. So case 1, suppose that P is congruent to 1 mod 4, or Q is congruent to 1 mod 4. So without loss of generality, we may assume that P is congruent to 1 mod 4. Now this is equivalent to the existence of an integer k such that P is equal to 4k plus 1. But then P minus 1 over 2 will be equal to 4k plus 1 minus 1 over 2, which is just going to be 2k. So it's always going to be an even integer. So therefore, if we look at P on Q, so now we're using the theorem statement, so we have P on Q times Q on P is equal to negative 1 to the P minus 1 over 2, which is now 2k, times Q minus 1 over 2. But Q minus 1 over 2, this could be odd. But what we know is it's something times 2k, which we know is already even, so this is just going to be equal always to 1. And so we got that this is equal to 1. But now with the Legendre symbol, we know that we have distinct primes, so this is non-zero. So it can only take the value of 1 or negative 1. And so we have that these are their own multiplicative inverse. So note that P on Q and Q on P are non-zero, and are multiplicative inverses of each other. And so therefore, because we're working now over the integers, we have that the only possibilities are P on Q is equal to Q on P, which is equal to 1, or P on Q is equal to Q on P, which is equal to negative 1. So these are the only ways that we can get 1 by multiplying these two. Either they're both 1, or they're both equal to negative 1. But either way, we get the statement we want. We have that these are both equal. And so that finishes it off for case 1. And now let's do case 2. So for case 2, we're going to suppose that P and Q are both congruent to 3 mod 4. So we have that both of these are congruent to 3 mod 4. Then P minus 1 over 2 and Q minus 1 over 2 are both odd. So I'm skipping a detail here, but the way we can see this is, because they're both congruent to 3 mod 4, when we write it in the form that we did over here, we have 4k plus 1 for congruent to 1. Now it's going to be 4k plus 3. Then this will be 4k plus 3 minus 1, which will be 4k plus 2 over 2, which upon simplifying will be 2k plus 1. So we will always get back an odd integer. And so I'm saying that part verbally, but we can go ahead. So we have that these both are odd. And so therefore the product is odd. p minus 1 over 2 times q minus 1 over 2 is odd. And so we get that q on p times p on q, which by the assumption, we're assuming theorem 116.11, this is p minus 1 over 2 times q minus 1 over 2. Since that is an odd product, we just get back that the Legendre symbol, the product of them, is equal to negative 1. And so we get this here. So consequently, but now since this is equal to negative 1, of course, we have multiplicative inverses, they're equal to negative 1. So the only way that's possible is if one is 1 and the other is negative 1. And so, in other words, one has to be the negative of the other. And so we get that q on p is equal to the negative of p on q. And so that finishes it off for the equivalence of 1 and 2 if we assume the homework exercise 11.3.12. So now let's show that 2 and 3 are both equivalent. So we're going to go ahead and show that 1 is equivalent to 3. And since 1 is equivalent to 2, that shows that all these statements are equivalent. And the way we're going to do this is, in the process, we're going to be showing that both of these statements are equivalent. So it's just going to be a string of if and only if arguments as we go forward. And so the first step is to define the following. So let p star be equal to negative 1 to the p minus 1 over 2 times p. And so the thing about p star is that it's always going to be congruent to 1 mod 4. Then p star will always be congruent to 1 mod 4. And so we can see this by cases. So we know p is either going to be 1 or 3 mod 4. If p is congruent to 1 mod 4, then we have that this p minus 1 over 2, by what we just argued, this will be even, so this will just be positive 1 times p, so p will be congruent to 1 mod 4. If p was congruent to 3 mod 4, then we would get that this here is going to be negative. And so then p star is equal to negative p. But negative p is going to be congruent to 1 mod 4, since p itself is 3, and negative 3 is 1 mod 4. And so that's the key thing. So we have that this p star is always going to be congruent to 1 mod 4. So actually, since I've said that out loud in words, let me go ahead and write this like this. So this is either p or negative p. So we have this here, and thus p star is congruent to 1 mod 4. So we got this here. And so now what we want to do is show that theorem. So we claim that theorem 1.16.11, so that, 0.10, is equivalent to p star on q being equal to q on p. And so that's going to be our first statement. So we're going to reduce what we want to prove. So this is the first of several string of equivalences that we will be showing, is that both of these statements are the same. So let's go ahead and see that. So now, if p is congruent to 1 mod 4, we know by the assumption that then q on p is equal to p on q. So in one direction, it's automatic. So if p is congruent to 1 mod 4, then we get that p star on q is equal to p on q, which is going to be equal to q on p. And so that's just the assumption of the theorem 116.10. So we have this here. So these agree. If p is congruent to 3 mod 4, then we're going to have P star on Q is going to be equal to negative P on Q. But now the Legendre symbol is multiplicative, so we have negative 1 on Q times P on Q. So now we're going to do this by cases, depending on when Q is congruent to 1 or 3 mod 4. So if Q is congruent to 1 mod 4, then negative 1 on Q is 1. And because Q is congruent to 1 mod 4, we just get back that this here will be 1 times P on Q, which will just be 1. So we get that, and so that'll just be equal to 1. And then we have that this is equal to if Q is congruent to 3 mod 4, then what we are going to have is that negative 1 on Q is negative 1. And then this will be times P on Q. But because we are assuming the theorem, so now this is the reason I wrote it this way. So here we have if Q congruent to 1 mod 4, if Q congruent to 3 mod 4. So Q congruent to 1 mod 4, this is, we establish as P on Q. And in the case of negative 1 times P on Q, because now P and Q are both congruent to 3 mod 4, our assumption is theorem 1:1610. So we have that P on Q is the negative of Q on P. And so now we have the negative, and then we have the negative. Q on P. And so these are both positive. And for the above one, I forgot to flip it. By the theorem, we also have this is Q on P. So in both cases, we have that this is just simply Q on P. And so we have now established that P star on Q is the same as being equal to Q on P under the assumption of theorem 1:1610. So now let us note the following. So theorem 1.16.10 is equivalent to the following statement. So we have P star on Q is equal to 1 if and only if P on Q is equal to 1. So we have this here. And so of course this is just a restatement of this equality. But what we claim that P star on Q is equal to 1 if and only if P is congruent to plus or minus beta squared mod 4Q for some odd integer beta. So if we show this, we are done. Because now we have P star on Q is equal to 1. This will be equivalent to P on Q, which will then, if this is equal to 1, then P on Q is 1. And in turn, we end up getting the equivalence with the theorem that we want. And so this is what we are going to focus on. So I've gone ahead and just wrote down what we have. So we have our definition for P star. And we know that theorem 1:16.10 is equivalent to this statement here. And so where we left off is that we claim this here. If we show that P star on Q is equal to 1, if and only if P is congruent to plus or minus beta squared mod 4Q for some odd integer beta, we are done. So let's go ahead and show this. So let's go ahead and assume that P star on Q is equal to 1. Then that means that P star is a perfect square, a quadratic residue of the integers modulo Q. So then we have that there exists some beta, some integer beta, such that P star, and so these congruence classes are modulo Q. So the congruence class of P star is equal to beta squared, that congruence class, in the integers modulo q. But now we want to look at minus beta or beta. And so the claim is that beta can be chosen to be odd. So since p is odd, since q is odd, one of beta or q minus beta is odd. And we do have for both cases that p star, that congruence class, would be equal to beta squared, which is equal to q minus beta squared, which is the same as minus beta. Oops. Didn't mean to put the parentheses there for the whole thing. So we have this. So we do have that this here. We have these equalities, a congruence class. So one of these is going to be odd for sure. So we may assume that our beta in the integers is odd. And so what I mean here is that we can go back to where we chose our beta, and now we can choose that beta to be odd. And so that's the one we're going to be working with. Our beta is odd, and moreover, we have that p star is going to be equal to beta squared plus q times L for some L in the integers. And so this is just saying, using the fact that p star is congruent, is equal to beta squared, is congruent to beta squared mod q. But we know that beta is odd. So since beta is odd, we have that beta squared is congruent to 1 mod 4. Now comes the Chinese remainder theorem. So by the Chinese remainder theorem, actually, hold on, I'm jumping ahead. So if we go ahead now and reduce this equation, mod 4, so then p star is congruent to beta squared, which is 1, plus q times L mod 4. So we have this here. But we already know that p star is congruent always to 1 mod 4. So that's the way we went about constructing our p star. So that it was always congruent to 1 mod 4. So we conclude that q times L must be congruent to 0 mod 4. So that's the only way that we're going to get back that p star is congruent to 1 mod 4. And so then we have this here. So QL is congruent to 0 mod 4. So the next thing we want to do is apply the Chinese remainder theorem. So by Chinese remainder theorem, so since p star is congruent to beta squared mod 4, so the QL goes away, so it's just going to be congruent to beta squared mod 4, and p star is congruent to beta squared mod q, the Chinese remainder theorem implies that p star is congruent to beta squared mod 4q. And now we are essentially done, because of course we have our p star, but we know that p star depends on the congruences on p being 1 or 3 mod 4. So let's come back to those definitions. So therefore, p is going to be congruent to, if P is congruent, it's going to be congruent to beta squared mod 4Q if P is congruent to 1 mod 4. But if P was congruent to 3 mod 4, then we will have a negative P on the left-hand side for P star, since that's what P star is negative P, as P is congruent to 3 mod 4. And so then we'll have negative P is congruent to beta squared mod 4Q. We can multiply both sides of that congruence by negative 1, and we'll have a negative beta squared. And so we got this here. And that finishes the proof, because what we have now done is a string of equivalences. Indeed. This here is equivalent to P star being congruent to beta squared mod 4Q. But now if P star was congruent to beta squared mod 4Q, then we have P star is congruent to beta squared mod Q. So P star is a quadratic residue modulo Q. So P star on Q is equal to 1, and so we have our chain of equivalences, and so that concludes it for the fact that all these statements are the same. And so the law of quadratic reciprocity, we have 3 different statements. So let's go ahead and finish off with a computational example. So what if we wanted to know if 7 was a perfect square modulo 19? Is 7 a quadratic residue of the integers modulo 19? What can we do? So we know by Euler's identity we will have that 7 on 19 is equal to 7 bar to the P minus 1, so here 18 over 2, so we're looking at 9. And so now we will have to compute this here. And so we'll have to take 7 to the 9, and then check if that's equal to, congruent to 1 or negative 1 modulo 19 to get that. But we want to be lazy for this. So what can we do? Well, the law of quadratic reciprocity. Because now we can go ahead and do the following. So if we apply the law of quadratic reciprocity as it's stated here, we can do the following nice trick. So we have 7 on 19. We know that 7 on 19, that both of these primes are going to be congruent to 3 mod 4. And so the law of quadratic reciprocity tells us that we can go ahead, flip this, and make it negative. So this will be equal to the negative of 19 on 7. So we got this here. But now we're working on the symbol on the top. So for the 19, we are working modulo 7 now. 19 is 14 plus 5. So we can go ahead, and this will be the same as checking whether 5 is a whether 5 is a quadratic residue modulo 7. But now we can do the same trick. We have 5 on 7. 5 and 7 are distinct odd primes, so law of quadratic reciprocity applies. But we know that 5 is congruent to 1 mod 4, so we can go ahead and say that this here is the same as negative of 7 on 5. So we get this here. But now 7 on 5, 7 is congruent to 2 mod 5, and so we have that this here is going to be equal to the negative of the Legendre symbol 2 on 5. And so we are reduced to asking, is 2 a perfect square modulo 5? And so then we can go through and check. 2 is not, so we will have to go, 2 squared is 4, 3 squared is 9, which is 4, and that's it. 4 squared will give us back, that's going to be negative 1, now just give us back 1. So this here is, 2 is not a perfect square modulo 5, and so we have that the Legendre symbol of 2 on 5 is negative 1, and so we have 7 is a perfect square modulo 19. And so we got our desired response. So for our last statement, we're going to come back to Euler's conjecture, and specifically this -3 on p is equal to 1, if and only if p is congruent to 1 or 7 mod 12. And so we're going to go ahead and show this statement here, and just recall that this statement was necessary for Euler for his proof of in 1759. And so this was a considerable headache to Euler to do, and we're now going to use the law of quadratic reciprocity to deduce it. So how do we show this using the law of quadratic reciprocity? So I'm going to go, in the lecture note, I do this the proof of this proposition in 3 different ways. So if you go to the lecture note, you'll find one argument that uses Theorem 1.16.10, and another argument that uses Euler's conjecture to deduce the desired congruences on P, namely P is congruent to 1 or 7 mod 12. Today I'm going to go ahead and just do the case when it's when we apply Theorem 1.16.11. So here's how we do this. So by theorem, we have that 3 on P times P on 3 is equal to -1 to the P minus 1 over 2 times 3 minus 1 over 2. And so that's just going to be 1. Oh, the eraser stopped working. So that's going to be 1. So now we have that this here is just -1 to the P minus 1 over 2. But we know from Euler's identity that this is just a Legendre symbol for -1 on P. So we have this here. So now we're going to go ahead and multiply on both sides by -1 on P. And so now we get -1 on P times 3 on P times P on 3 is equal to -1 on P squared. So we get this here. But now over here, we're going to have that this is going to be the Legendre symbol of -3 on P by the multiplicativity times P on 3, which is equal to 1. But now the only way that this here is equal to 1 is if -3 on P and P on 3 are both 1, or -3 on P and P on 3 were both equal to -1. So in other words, if both of these were equal to each other, and so we have that this here is the same as this here. But what we want is -3 on P. And so the hard part here is that we're working over the integers modulo P, but this is telling us that that's precisely those primes that are perfect squares mod 3. And so for that to happen, those primes when we reduce mod 3, that they are perfect squares. But now this tells us that P has to be congruent. The only perfect square modulo 3 is 1. So P is congruent to 1 mod 3. Okay, so that's good, but that doesn't get us to the 12 over here that's appearing. But that's easily bypassed because we know that P is an odd prime. So since P is odd, we have that P is congruent to 1 mod 2, and by the Chinese remainder theorem, we get that P is congruent to 1 mod 6. But P congruent to 1 mod 6 is equivalent to P being congruent to 1 or 7 mod 12. And so in the case of Euler, he was working with his form of the conjecture, which had it 4 times q. But the way that we are approaching it, we don't need to go that far. Because as we see, we know that all we need is p congruent to 1 mod 6. And that will tell us that all the primes were the form 1 plus 6k. And so working modulo 12, the only other possibility is 7. And so now we have concluded the statement for when negative 3 on p is equal to 1, what are exactly those primes? And so we have done it in an easy fashion by applying the law of quadratic reciprocity. And as I mentioned, in the lecture notes you'll find 2 other proofs for the same proposition using the first statement and then Euler's conjecture itself. And so next time we're going to go ahead and start laying the groundwork so that we can prove the law of quadratic reciprocity.